Our presenter today is Andrew Kiggins. Andrew is an SDM with IoT Security, AWS IoT. Today with us, we also have Nicole, Gary, and Ramkishore. They are our webinar moderators who will be engaging with you and answering your questions throughout the presentation. Andrew, welcome. The floor is now yours.
Thanks, Question. Welcome, everybody. I'm really excited to be here to talk to you about IoT security. Obviously, IoT is really big, so I want to cover some of the security risks and the issues that we're seeing out there. Talk a little bit about the IoT best practices that we're looking at and things that we've got inside AWS, and then dig a little bit into some of those security mechanisms that you want to be aware of. And then a little bit about some of the things that you might want to do as a manufacturer of devices or a user of devices. What are we going to cover today? Today we're going to have a quick overview of IoT. Then we're going to talk about some of the risks that we're seeing out there in the wild. And we'll talk about how we can protect communications between your IoT devices. And then talk a little bit about the devices themselves. So as you're probably aware, there's now millions and we're heading towards billions of connected devices in the IoT ecosystem. And they run the gamut from your Fitbit on your wrist all the way to your wired car, to blood pressure monitors in hospitals, to controllers and thermostats. They're really becoming very widespread. And that poses very interesting security challenges, both from the environments that these devices are deployed in, as well as the massive surface area that criminals and adversaries want to take advantage of. So IoT is becoming really important, and the mechanisms that we use inside the security space are getting a lot of visibility. So I want to take a quick look at the AWS IoT ecosystem and how it comprises of. From the left-hand side there, where you've got your device SDK that you deploy in your device to be able to upload and connect through the authentication and authorization system, and then into the device gateway to ingest messages, and some of the things you can do in the back end in your rules engine to modify and transform those messages and take advantage of other AWS services. But what I want to focus on today is really authentication and authorization and the security mechanisms behind them, that we can make sure that we understand who's talking to whom, verify their identity, make sure that only the messages that we want to transmit between devices or between device and server are actually the ones that are being sent, and that in fact that they actually get there in the format that we expect, with the information and with high fidelity. If you've followed any of the other webinars or had a security conversation with any of the AWS folk or the security professionals in AWS, you'll have already heard about the shared security model. AWS's commitment to our customers is to protect the cloud and things of the cloud. That means our services, our infrastructures, our data centers, and all the underlying mechanisms that support them. When customers bring their applications and their services to the cloud, there's the responsibility of the customer to use those services correctly, to use encryption, to use policy, to use identity and users groups, to make sure that when you deploy your application or your service into a cloud environment, it's as secure as it possibly can be. And we're going to touch on that a little bit later on as we talk about some of the things that you can do as an AWS customer, as a user, as a builder or manufacturer of IoT devices. So, what are these possible risks? There's three main ways that an adversary could take advantage of the IoT ecosystem. At the top there, one of the things that they can do is not corrupt or steal your data, but simply snoop on your data. And that's really interesting environments where that data has a very high value, and there's possibly competitors or other criminal activities who could make use of that information to your disadvantage. The second thing
is losing control of your device. And that's the one in the bottom left-hand corner, where someone actually gets into your device and takes control of it. We saw recent activity a bit like that with the Mirai botnet, but there's many other potential uses that a criminal or an adversary could have if they take control of your device. Sending false telemetry, deleting your data, causing that device to behave in a way that it affects your infrastructure, or giving access to other servers further in the network. The third thing is masquerading as a device or a device type that you own and think you're in control of. And in that case, they could be injecting bad information, they could be masking some behavior that you want to monitor, and generally corrupting the data that you're relying on from your IoT devices. So how do we secure these? How do we secure that data? Well, one of the things that a lot of effort's gone into is protecting protocols that are used to transmit the IoT information, the data that's critical to our business systems as it goes across the network. And there's a number of ways of doing this. In IoT, we support a number of protocols. MQTT over TLS, MQTT over WebSockets, and HTTPS. Depending on exactly which mechanisms in use, there's a variety of ways that we can do authentication of the client and the server, how we protect the confidentiality of the data and how it's transmitted and encrypted, and then the various protocols that are actually supported in that mechanism. And it's important to understand that not all mechanisms are applicable for all classes of devices, and not all devices have to support all IoT protocols. It's very much pick and mix depending on your use case and the type of device that you want to use. And we'll come back to this in a little bit. The next thing I want to talk about is how you actually look at the device from an identity standpoint. How do you actually make the device known to the system and establish who that device or person really is? And there's a number of ways we do this. From the device standpoint, we rely on certificates. Traditionally in AWS, a user or a role has credentials, and we support a similar mechanism whereby you could use AWS credentials to access the IoT. You could also use the same credentials in theory to access other AWS services. We also support mobile applications through Cognito and Cognito Identity, whereby with integration to STM, you can get tokens and credentials issued to your mobile device, which you can then use to access IoT. Individual users can use their security credentials and, based on their IAM policies, interface with the IoT APIs. Of course, this is all built in one cohesive system where policies and rules and identities are all working together to provide you the security that you need to safely interact with IoT and ensure that your devices can be recognized and can transmit and receive the data that they need. Identity is handled in three basic ways. X509 certificates identify devices. IAM users, groups and roles with the corresponding credentials can be used at the application layer if you're using HTTP or WebSockets and you're running requests across those. And Amazon Cognito identities can be used for API level access. So, how does the authentication work? Authentication for IoT is mutual. The server authenticates the client, The client authenticates the server. This is really important because you have to make sure as a device that you're sending data to the servers and the endpoints that you expect. From a server standpoint, you want to ensure that the device that's transmitting you data is really who it says it is. So verifying the credentials that are being presented is really important. And this really isn't an AWS thing. These are our standard technologies and encryption mechanisms based on TLS that are used throughout many, many industries in many different types of situations. Fundamental to this is, of course, keys and the protection of keys. So the generation of keys, represented there by the little red key, is really, really important, and the protection of those keys is also important. So making sure that those private keys are protected on the device is the job of the customer, just coming back to the shared security model. Ensuring that keys are protected in AWS is AWS's responsibility, and we protect those keys very carefully. On top of that, we use the strongest cipher suites, and we'll talk a little bit about this later on. It's very, very important that mechanisms are kept up to date. The protocols, the cipher suites, the strength of the encryption mechanisms, to make sure that some of the latest mechanisms for trying to crack these are blocked. There's a number of ways of generating certificates and getting them onto your devices, and we're talking specifically here about the device side. The server-side certificates are obviously handled by AWS through our server-side certificates, so that you can be sure that you're connecting to an AWS server point end. But generation of certificates for devices can be done in a number of ways. The first and the easiest to use is simply letting AWS do the heavy lifting for you. AWS will create your private public key pair and will handle the certificate creation for you as well. Of course, the downside of this is that at some point that private key has to come out of AWS and be burned into your device. The second mechanism is whereby the device manufacturer brings the certificate, either installs it into the system or has AWS create a certificate for it by issuing a signing cert request. In this way, the private key is never given to AWS, so there's never a chance of it being lost in transit. So that's a slightly more secure, but of course there's a slightly greater overhead. The third mechanism is where certificates are created on the fly in the devices and authenticated when AWS first see it. In this case, there's no explicit API for the certificate to be added to AWS. A customer builds a CA or installs a CA on AWS, which is responsible for signing these certificates. And the first time that certificate is used to connect to AWS, some back-end processing is done to authenticate the device. AWS understands that that certificate has been created by a trusted CA that the customer's provisioned, and then a Lambda function can be called to authorize that device into the ecosystem. Of course, the Lambda function is under the control of the customer, so the customer gets to choose which devices get in, which devices get out. For example, if a certificate's compromised, the customer may choose, and probably should choose, not to allow that device to connect. So it gives more control to the customer at the overhead of a little more development and coding. One of the things to be aware of with certificates is that they're time-bound. A certificate, when it's created, may be created for future use. It may have an expiration date. And it's very important to understand that certificates, when they come into play, are available and usable at the time they're expected. For example, if you create a certificate in the future and that device tries to connect, it's going to be refused. If you rely on the device to connect to an NTP server to update a timestamp, and the timestamp's not valid because you can't connect the NTP server, you get into a chicken and egg problem. So it's very, very important that timing is handled correctly and that your devices have a clear understanding of what time it is right now. There's other ways to handle it. Not validating the timestamp on the certificate if the device has been out of service or on the shelf for a long time is one day, or not validating the timestamp if you've never been connected to an NTP server, and that gets around the problem of the device not understanding time. The next thing I want to talk about is authorization. It's all very well having all these devices connecting to your network, but how do you control the flow of data? So as I mentioned earlier, AWS IoT supports policies, and policies can be used to control how devices behave and how they interact with the IoT servers. This is an example of a policy. It comprises of 4 main parts. First, what does this policy allow or deny? The effect. You can deny explicitly access to certain topics, or you can explicitly allow. The action is the thing that tells the server what the device is allowed to do. Can it publish, for example, in this case? Can it receive? The third thing is the principle. What is the operation actually acting on? And in this case, we can see it's a topic. So this policy essentially says, I'm going to allow publishing to this topic for all things that have a name corresponding to this type. And that comes to the fourth thing, substitution. You can substitute various types of variables into your policies that allow much better control at a global level of what the individual devices can do. Now, the other thing to note is that policies can be attached to individual devices. A single policy could be attached to many, many different devices. There's deeper levels of policies and how you use them. It's a whole topic unto itself. So if you really want to understand more about policies, there's plenty of really good resources from reInvent talks and blog posts that go into the depth of how they allow and they deny effects, interact with each other, and default behavior and evaluation. An example might be, in this case, where you've got a policy attached to various certificates that tell which trucks can upload telemetry and which trucks, for example, can do other actions. Maybe truck 1 has very simple policy which says all you can do is connect to IoT and publish information. Truck 2, maybe the master truck, maybe it's allowed to subscribe to various topics as well and receive information. And maybe truck 3 is the controller, so it has a much, much greater number of actions. So you can choose multiple actions, single actions, or a variety. Just going back here, in this case, we could actually put in under the action IoT:**, and that would allow this policy to give all actions to the certificate on the device that it was associated with. And this is the total list of policy actions. These correspond tightly to the various actions in the MQTT protocol. So I mentioned encryption. So let's have a little history lesson of how we got where we got. So back in the day, SSL 1.0 was developed, and as luck would have it, it was never published because it was full of bugs and full of holes and really wasn't very good, which fortunately they realized very, very quickly and came out with SSL 2.0. Over time, various features have been added, additional encryption mechanisms, additional encoding mechanisms, new ciphers, new algorithms. So over time, SSL has developed with SSL v3, became TLS 1.0, TLS 1.1. We're now using TLS 1.2 in most places, and TLS 1.3 is underway. You've probably heard of some of these Heartbleed, Freak, and Poodle vulnerabilities that have been discovered. And what happens when those vulnerabilities and exploits are created is that the protocol evolves and there's patching. And it's really important to keep patching our cipher suites and upgrading our protocols. And this has actually started to lead to industry and vendors and compliance regimes such as PCI DSS enforcing strict adherence to the strongest ciphers and the newest versions of TLS. An example is Apple, who have their ATS protocol, which is now mandatory on new application development to enforce the use of TLS 1.2 and strong certificates in the strongest ciphers. In AWS, IoT only supports TLS 1.2. The client-side certificates have to be of a certain strength. You can't use a 1024 anymore. 2048 is required for RSA. For the elliptic curves, we use the strongest curves. We also have recommended cipher suites. There is actually a fuller list of cipher suites are supported. Obviously, one of the issues is that there's many older devices that may not be upgradable. They may not have the capability or the capacity for some of the stronger suites. Very small microcontrollers that are restricted in the amount of RAM and CPU may simply not be capable. So we're very aware of backward compatibility issues, of how we support older versions of devices that are out there. And also, we want to ensure for Diffie-Hellman that we're using the strongest primes or the largest primes. There is some literature out there that says that 1024-bit primes are no longer secure, and certain state agencies can actually break those. So we want to ensure that we're using the strongest bit primes to make sure that the data is protected in transit. So that's some of the things that AWS is doing to protect the data and the services and enforce policy on the data. But as a customer, what are the things that you should be thinking about? When your device goes onto the internet and has public internet access, you can pretty much guarantee that within 15 minutes, probably less, someone is trying to scan your device to find out how they can compromise it. Now, with the smaller real-time operating systems and the small microcontrollers, there's very few ways you can do that. It's a hard thing to do because there's fewer open ports, there's fewer well-known exploits. But obviously, as IoT systems develop and we start using IoT gateways, those things tend to be built on more powerful operating systems like real-time Linux, which are much more capable and have a much more attackable surface area. So, as you develop things, you have to figure out how do I protect systems. Now I mentioned private keys and how you protect private keys. So there's many ways, and one of the important ways that we see out there in the industry a lot is hardware-based solutions. Going so far as to burn that public key into an EEPROM and then burn the fuses that control that EEPROM. So essentially it's a write-once device, so that once that private key is burned in, it can't come in and it can't go out, and it can only be used for encryption. So obviously that comes with some expense and some complexity, but it is something we're seeing a lot out there. Then of course you have to consider, how are you securing your certificates? How do you get your certificates onto the device? How do you ensure that no one else has access to them? How do you ensure that once they're installed they can't be extracted? So there's a number of different mechanisms that we've got customers. Obviously many customers are having their devices manufactured overseas, so there's very strong security mechanisms put in place to control how those certificates are being burned into the device. We talked a little about just-in-time registration, so it's only when the device actually connects that that certificate's used. And then there's some other work underway and some very good mechanisms that we've been more than happy to talk to you offline about. So, how can you identify things on your system when it's on the public internet? Pen testing. Just as you'd pen test your laptop or your corporate network to find out what ports are open, what applications are running, pen testing can tell you very, very quickly what the vulnerabilities are of your device. And this isn't just at manufacturing time. Understanding, is that device secure as it goes out your manufacturing facility, is really important. But being able to actually pen test on an ongoing basis is really important, because security is not cast in stone. It's an evolving thing whereby there's new security threats, new mechanisms, operating systems are being patched, new exploits are being found, new workarounds are being found, new mechanisms are being developed. So in-service pen testing is really, really important. For the more powerful operating systems, such as real-time Linux, you can be running a vulnerability scan, understanding what applications are installed, what libraries, what kernel versions you have on your thing, and what level of security they have. There's very well-known databases of vulnerabilities, the CIS and the CVE, common vulnerabilities and exploits, that are able to make evaluations based on the information about the state of your system. And finally, telemetry. We talked a little about the Mirai botnet. Do you actually know as a customer where your data is going to? Can you tell if that device is talking to who it's supposed to be? Is it contacting the DNS servers that it's supposed to be? Or has it become part of a botnet? So understanding the data flow from your system and where it's going on the internet is really important in understanding whether your device is behaving as expected or whether there's some abnormal behavior that you need to take a deeper look into it. So that's really IoT security in a nutshell. There's more information there on our internal web pages. We've got some excellent blog posts. But at this point, what I'd like to do is actually go on to a little bit of a demo, because a lot of this is really, really simple. So let me crank up my internal website, and this is my console. And I want to talk through how you could actually register your own CA inside AWS, and how you could use that to generate your site. So I'm going to click back a little bit. This is the IoT console, and you see there's lots of stuff going on. We've got a registry, and I want to focus on security here. So as you can see, I don't have any CAs yet. So what I want to do is I want to register a new CA, and it's very much point and click. So I don't have a CA certificate in my account, so I'm going to register one. And it's a really, really simple interface, and it actually walks you through the entire process of how you go about generating your key pair for your verification, and then how you actually use that to verify that the root CA certificate that you're going to install actually belongs to you. Because obviously you could go out and get a certificate, present it as your own, and it may not really be yours. So this step generates a certificate. So let's just cut and paste this, and I'm cut and paste because my typing's not good. We're going to go over here, and as you can see, I've actually got my root key and my PEM file with my certificate already installed. So I'm going to generate a new verification key. There we go. So it generated me a new private key. Now this is really important. This is the registration code that AWS provides to you so that it can verify that the certificate you're presenting is actually bound with the request that you're making. So you need to save this one, because you can use this multiple times. So for example, if you were automating this, you might want to save it in a file. So I'm just going to save it very temporarily in this file if I ever needed to use it again. And I'm going to create that CSR, certificate signing request, with the registration code that I got from this step here. Oops. So country, well, that'll be Scotland. Province, we'll call it Lothian. And locality. Organization name sudo AWS. We don't have that, although I suppose we could call ourselves IoT. That's where. Now the common name is really important. So, and this is the key thing. In this place, this is where we want to copy this registration code, because that's the thing that links this certificate request with the root certificate we're going to present. So it binds the accounts together. So we can type that in there. Email address, well, we can skip that. This is an optional extra. If you want to set a challenge password, again, optional, we can just skip over that. And now, we can see we've got our CSR. So I'm going to combine these together with my root certificate. Don't ever give this out. There we go. So I type in my password, my passphrase for my key. And now you can see I've got my verification cert and I've got my root file. So now I can upload my certificate. Okay, so I go and click on my root cert and I upload that. And now I'm going to click on the certificate I just created with my verification certificate that yes, I really do own this account and this is my root certificate I possess. Now just a matter of interest, that root certificate was something I prepared earlier. It's not a real root certificate, but there's no reason it couldn't be a private CA cert that I want to use. And I add that in. Now you can activate it automatically or you can save it for future use. And then there's another button here called Enable Auto Registration. The Enable Auto Registration feature is for that just-in-time registration feature I talked about earlier. So if I enable this and I click Register Certificate, it's succeeded. We can see it's enabled. You can see there's some random information there. And it's got some default registration expiry dates. And if I go back to that, I can now see I've got the certificates. I can select that. And I can go and look and see what things I can do with it. So I could deactivate it if I suddenly decided or realized that that certificate had been compromised. I can disable my auto-registration so that auto-registration doesn't happen anymore. And the auto-registration was that thing I talked about earlier on, where devices that have their certificates signed by this CA can be auto-registered the first time they present that certificate. So that's a feature you can enable or disable, and you're going to get a prompt just to make sure that you're doing it. So that's it. I've got my certificate of signing authority, so now I could go back and start using this CA to actually generate certificates and use them from my IoT device.